Thank you, organizer, for the invitation. I'm going to present something so-called topological Laplacian and try to argue why this thing is actually working better and have some power in the real world life application. The real life application we are interested is actually, you see, maybe you can see here, there's like FDA, things like Pfizer, BMS and NIH and those type of domain. So I'm not change the page for some reason. Something broken this. Oh, I see.
Yeah, we can now show you.
Yeah, okay. Yeah, thank you very much. We actually tried to do data-driven biological discovery. For such a things, we actually similar to other people. We do all kinds of different type of biological data and pass all kinds of different machine learning algorithms. But on top of that, actually, we also doing a lot of measurements. So yeah, so we do different geometry, algebra topology, and even sometimes we do geometry, algebra, so on and so forth, and try to looking for what is the best algorithm for real world application. So I will show you some real world application. Also, we combine the whole thing with machine learning, all kinds of different machine learning. Pass even something we actually particularly interested, like topological deep learning. I think this, yeah, like a topological deep learning. This is something we particularly interested. We actually probably proposed the first topological deep learning and put the word together in the 2017. So I don't want to waste your time talk about topology, but just try to say, even just a few years ago, there's a Nobel Prize for topology. That's a low-dimensional topology, slightly different, but it's more general sense of topology, like a chain mail, things like that, Yeah. I don't think I needed to go through this material because this actually was prepared for people in the biology or chemistry, right? So there's all kinds of topological representation, particularly we heard about in the morning, topological diagram and topological like landscape, things like that. But what is the limitation? People know the topology has a limitation. You cannot distinguish between a mark and a muffin. So that's some problem. Means you need to keep looking for something more powerful, and that's how persistent homology is come up on top and become so popular and driving the TDA in the past 2 decades. So I don't want to go through this theory and why the arguments about persistent homology. Again, this is for people really outside the field and try to show them, impact them, impress them with some type of simple geometry and see how things are going. I don't want to go through this things in the next 1 minute to see those type of Betty 1 and Betty 2, they are cure things like that. Maybe I can just go a little bit like a fast forward for this one. Right, and how to use it for biology? You see, this is something so-called alpha helix. Is one important thing in the structure biology. So this is the C alpha compounds over with the helix, and then you see the Betty 0 and the Betty 1. There are 4 of them at a certain particular filtration parameter. You can have a Betty 1 over there, and then if you add one more thing there, you can see how they are systematically grow. And if you add more, so you can systematically have those things for the whole alpha helix. And also for basic barrier, there are basic structures in the biology and also in the microtube, things like that. This is a type of things we can do with the Poisson homology. And we can also do it with the dynamic system. For example, this is a protein folding inverse process of the protein folding. And you can see this is the cam and this is a radius filtration. You can see you have a two-dimensional representation for this is extremely high dimensional problem. It can be tens of thousands of dimensions over there, right? So that's how the method is very powerful. Finally, just need to analyze this part instead of go to like 15,000 of dimensions. But however, we have enjoyed so much success in the past 10 years or so or more in terms of application for TDA or Poisson homology to real world problem, particularly for biology. I will show you a little bit later. But what is how to improve these things? Is there some limitation? The answer is yes. So it cannot handle the heterogeneous information. For example, different type of things in the data. You have a point cloud, you assume everything in the point cloud are equal, but actually it's not, right? For the people in the room, you have a man, you have a female, things like that, you have a senior, you have a junior, whatever. There's a lot of homogeneous object over there. So in the point cloud. So, and also you see it's a quantitative rather than qualitative. So you can see like a 5 number range is counted the same as a 6 number range. If you go to biology, people throw you out of the room, you say those are equal, right? Because they make so much different function. And also cannot distinguish non-topological chain, like homotopic shape evolution. I was using example to show what is that exactly. So, and also is incapable of dealing with the directed network and the diagrams, like polarizations, regulation and control issue, and organization, like a university, you have a president, you have a college dean, things like that, department, you have a chair, just organized system instead of everybody is equal in the point cloud. So you have to address those things with things like a hypergraph and a digraph. So those are the type of things we are interested to try to have motivated us to come up with a better method to deal with the real world problems over there. So one type of thing one can do is something so-called persistence core homology. That's actually enable you to see here. There's a different chemicals over there. The red guys, for example, oxygens and blue guys, nitrogens and carbons, things like that. And then you want to incorporate those information into your barcode representation. That's why you have a colorful barcode. You see, so it depends on the origin, things like that. And then in order to do that, actually, we also try to Wasserstein and optimal transport techniques over there. Something we did quite a few years ago. And actually, we were quite successful use this type of approach. This is the one way. Other way is to try to see, go things from a so-called combinatorial graph. Topological Laplacian is one example for topological Laplacian. Also, again, I don't want to go through this because it's a simplest and the chain group boundary operator. After getting into boundary operator, what you can do is just try to construct the edge and join the boundary operator from there. And then what you need to do is try to actually have a Q combinatorial Laplacian operator. So use those boundary operator and join the boundary operator. So it's constructed in this particular way. This actually has the advantage of giving you something. I give you the Betty number from the kernel space for this type of formulation. So the kernel space is giving exactly like a Poisson homology would like to give it to you. But the non-kernel space or the so-called non-harmonic part actually give you the actual information. I can show there with this example, you see. That's how wise this is allowed in the persistency. So that means the filtration in this way. So you get original 6 number range like that, you do filtration, you can see the Betty 0, there's no Betty 1 at this stage, and then you keep increasing your filtration radius, that's what you have. So you have something, you have a ring, so that tells you, you have a Betty 1 come out. So the blue ones are the Betty numbers, the red ones actually the long harmonic is so-called long harmonic non-zero eigenvalues, put in that way. That's what put the first non-zero eigenvalue over there for Betty for the dimension 0 and the dimension 1 space. So you can see this blue ones, they have a show, this have a ring, anything. And then from that further, you don't see anything blue things change, right? There's no thing. But what happens if you go further in the filtration, you see? So there's no thing change topologically. But however, at this point, you see more connectivity. So this more connectivity is so-called homotopic shape evolution, what I refer to. The shape evolution over there, you have a change in the shape, you have more connectivity. Topology does not reflect that part. You see, you don't see that things. You just see something disappear. And then you go further, you see since more further connectivity is established. This is particularly important for biology for network. In such a case, you see other things come out. There's in addition to the blue part, it's original person homology would tell you. The red part told you a lot of difference. The more signature come out from that. So this additional information are crucial for biological application and even for other applications. If you want to detect a terrorist group, things like that, you want to see how many people in the group, right? So you have a ring over there, 30 people, that's different from a ring of 30 million. That's a huge army, right? So, but the topology tells, oh, that's the same thing. So that certainly doesn't make sense, doesn't help the Department of Defense to make a decision, right? So this is the type of topological things we try to develop. And also we use something so-called a path Laplacian. So this is a part of the path Laplacian. You see, this is a so-called path Laplacian or path homology. People have been doing over there. And this is the other one, you see. So if you see the blue part, again, the Betty 0, Betty 1s, over there, the blue ones are the same for this two. But for anybody, even element school kids below, this is so different things out there, right? So different. But the homology part, the path homology part doesn't tell you the difference. But the Laplacian part, actually, you can see the difference, the red ones. So that's why this type of Laplacian give you a lot of more information you need to understand what's going on. In addition, we're also looking into a sheaf Laplacian. The reason we want a sheaf Laplacian because it enables us to actually embed physical laws like a Coulomb interaction in the topological representation. For example, I have a different charge all out of there, right? Think this is the charge or a different way, And in such a case, you want to use this algorithm to actually embed those information into the topological representation. That's how the sheaf theory can help us. So, and certainly when we talk about the sheaf theory, we know Robert, he actually grasped, he does a lot of things like that, particularly his group, right? So we actually tried to see from the sheaf theory, you also can see they actually can distinguish something with so-called a homotopic shape evolution and connectivity in a system. It can actually reflect that part. So this is how we are interested in this type of things. I think I needed to speed up a little bit, yeah. So we're also doing something like a hypergraph, like with other people, like Genu is in the group in the audio field, and also hyperdigraph, things like that. So the hypergraph and hyperdigraph. They are similar type of things trying to show you the internal organization, like directions in the system, and how many people they form a small group, and with the leadership who is pointing to who, things like that. And those things, again, the blue ones are just the homology part, and the red ones you see there are more jumps over there in the red part. That's the Laplacian part. Yeah. So basically, I'm done with this type of things. I just wanted to move a little bit further, like the Rham-Hodge theory, because everybody knows like Hodge Laplacian did the connection with the algebraic topology. I don't want to go through these things because out of the time over the day. But basically, we use this type of things for biological systems. This is something we did a few years ago, and for the real like cryo data analysis, things like that. But we also go a little bit beyond that. Basically, from the observation, basically, if you combine algebraic topology with multiscale analysis or filtration, in the middle we have a persistent homology. We know that, right? And then if you combine algebraic topology with differential geometry, you get something so-called the Rham-Hodge series. So things like that, because there's algebraic structure behind the differential operators, things like that, right? So, and then in the middle of this two, you have something mathematically manifold convergence. There's quite a lot of pure mathematicians work around there, right? But what is in the middle, right? In the middle of the input, nothing there. So and then we realize, oh, in the middle must be something very powerful, something very useful. So that, and then we did something so-called evolutionary Rham-Hodge series. It's basically it's a different way, say, persistent Rham-Hodge series, something like that. But since we deal with the manifold, that's why we say it's evolutionary, right? And these things certainly can motivate from things like that. There's a low change. You see, this is have a different sound over there. There's a low change in the topology, but there are always a change in the geometry. And in particular case, like a topology type of tools doesn't work, but a geometric tools does work. So you can go through the same type of construction, try to find out those type of ground complex, things like that, and use a manifold evolution, things like that. In this way, we actually can see if you have a molecular over there are some type of topological change. So this is the Betty 0, this is the Betty 1 part, this is the Betty 2 part. And you see the blue parts are actually the blue part is let me see. The blue part is the person homology or type of information. And this is the non-zero frequency. You see, the non-zero frequency actually keep changing. So even topology does not change, the frequency always changing. And also at a singularity, you change in the topology, they also have jumps over there. So that means this type of method, they actually can give you more information, right? So I basically gone through all the mathematical tools I wanted to talk about. Certainly this is come out from quite many papers, right? It's not one paper. I'm not presenting that, just presented the idea, what is important, what is not important, what is needed to be improved, put it that way. Yeah. So I wanted to use the rest of my time, try to show you some application we did in the past. I mean, this is something we did actually some time ago with some type of mathematician. They are all in the math department now. They actually will participate in all the wide competition in the drug discovery. So we compete in the drug design, something like that. If you see a gold, things like that, you see, that means we are the #1 over there. And initially we only get 1 gold, and the next time we get more gold. And later we just get too many golds, you know. And even the organizer feel somehow is just intimidated with our performance. They actually come up with a lot of different categories, was not initially announced. Otherwise, the whole thing dominated by us. So this is the things I just try to show the topology so powerful. If you write a proposal, you don't feel comfortable to say topology is the best technique over there, you just refer to our work and convince the people, say our topology is the best, you know. So we have a lot of more evidence to show a lot of this drug discovery competition. There's so many smart people out there because the drug design has a big money, right? They are about $200 billion per year on the drug discovery. So you see how many people go there, you know. So this is the pandemic, something relevant to everybody. We still see people in the Moscow, right? Something like that. But it's simply true for the pandemic. You see just a few bumps, right? Alpha, beta, gamma, and omicron, and beta, BA2, and BA4, BA5. And this is how many people getting infected in terms of millions every day, each day. So you see that this is a signature for the pandemics, good summary. So what is this is relevant? So when you try to understand that, we try to do mutation analysis. We look at all the mutation, look at the genetic data, keep the meanings of mutation, put it over there. We have many people doing this work. So in the past 3 years, but you don't see anything, just random. That's what one word you want to come up with, right? So, and then if you look into mechanism, you see there's a lot of molecular mechanism, and also organelle level, there's a mechanism, and then there's a population level, there's a lateral selection. So at the end of the day, you realize that's easy. That's a competition of 10 different mechanisms over there. Even for those people in the biology or in the various study domain, they don't know what's really going on, you know. So, and then we look into something like that. This is how a virus can get into the human cell. You see, this is the human cell. Well, after getting into human cell, they actually have all kinds of different processes. It takes the whole community, research community, next 50 years to really understand what's really going on. But on the other hand, it's simple. This virus just want to assemble their material and come out of here to infect more people. That's what virus wanted to do, right? But for this process, it's so complicated. So how can we make sense of out of that? The way we try to make sense is to say this is an interaction. So it's a protein-protein interaction. And if no such a protein interaction, the virus is never going to actually infect us. So we look into protein simplified power into just two proteins interact with each other. So and then we use the topology for that. That's the story. Okay. And then let's see what we did. We actually predict things all the day at run of time. We predict the most important size in the 2020, and we say those size like those ones going to be have a significant chance to mutating into significantly more infectious co-ligands, so strains. So this is 3 years ago, and this is what we know now. All the importance like alpha, beta, gamma, delta, epsilon, you know, Omicron, and all other things, they actually show the ones we predicted, the bindings, the mutation side is there, you know. Everything is actually captured by us 3 years ago. So this is what happened right now. And also we actually say that at that discovered mechanism, actually we say the natural selection is a mechanism. Look at the mutation, which mutation has more population, you absorb more times. The red ones are the ones the mutation make the virus more infectious, and the blue ones are the mutation make the virus less infectious. And then the natural selection make those ones have a more chance to be absorbed. So, and this is the so-called natural selection. And that's the mechanism we discovered actually also in the 2020, long time ago. Right. So that's the mechanism we discovered, and it was certainly based on the topology. I will show you with one slide later on. And the second mechanism we discovered is something so-called vaccine breakthrough. So this is a look at the different mutations, and the color means their population, how many. And then we found out one particular mutation actually make the virus less infectious. However, the population is still very high. So, and then we see this one particular mutation out of the how they are correlated with vaccination. Initially, we have an vaccination like Denmark and the US, they have a 2-dose vaccination, and that's the frequency mutation. They are actually have a very strong correlation. And that's how we found out that there's a second mechanism out of the in terms of natural selection, right? It's due to the vaccine breakthrough. Actually, our group was the first one to find out those two mechanisms. We actually have some prediction at February 10, 2022. We say this one particular BA2 is going to high potential to become a less dominating variant. That's what we said at that time. And then you can see later on, this is a WHO, they announced this one become dominant. You see, a couple of months later, something like that. So we actually can forecast which variant is going to become dominant in the future. We not only did that, we also did the other one. On the May 1st, we said the other one there. And then you see WHO also confirmed that in 2 months later. At this is the point that we say this part is going to become dominant. And this is the point that really become dominant. This is about 2 months apart. So we actually able to predict what is going to have a new variant over there in the infection 2 months ahead. So this is how we did it. We did a user, you see, patient data, and then we do genome sequencing and genome typing, find out what type of mutation, and look at the virus and the human protein interaction, and then incorporate this information into barcode representation. So this is the particular barcode, and then we use deep learning to do the prediction. So that's what we did with this slides. Since I got maybe 1 minute, so yeah, actually it's good. This is our collaborator and our group and our people, and also we are looking for quite a few postdocs there. Right. Thank you for your attention.
For a great talk. Questions?
Yes.
On the first half of your talk, you had the non-harmonic spectra. There was eigenvalues on the graph.
Yeah,
Can you
exactly.
say more about those eigenvalues?
I see what.
What's the intuition for the?
Oh, those.
Yeah,
I mean, the first
increasing.
eigenvalue tells you the so-called algebraic connectivity. That's typically mathematical people think about that. So that's an indication that how more quantitative what's going on with your system, right? Yeah. So like a bridge, right? How to build a bridge and such that you run a car over, it won't collapse. So that's the first eigenvalue you look into that. Yeah.
No questions?
Oh, sorry, go ahead. So the theory of persistent Laplace is well developed now. It's settled that there is a distinct notion of persistent Laplace now.
Oh, I think Yuso and Facundo, they recently have a paper. They have a couple of papers on that. It's jumping, and also other mathematicians analyze, like Jiu in China, he analyzed that part, and also Jiu analyzed. So the series, don't think it's settled. There's a lot of things to do. And also, I mentioned about 5, 6 different Laplacians. A lot of them nobody has studied.
Yeah. And your results, which has really, you can predict all those data and diseases. Did you use the persistent Laplace?
Oh yeah, I use the persistent Laplacian. One of the title of the paper, it says persistent Laplacian projector, right? So this is the type of paper, you see. I really use the persistent Laplacian. The title says the persistent Laplacian projector. The reason this one give you something around 3% or more, it's become more accurate, higher accuracy, compared to ordinary persistent homology. Sometimes 3% is so that determine which method is the dominant method, right? So we actually use the persistent Laplacian out of it, right?
So you said that at the end of the pipeline, you fed things into machine learning algorithms. What's the training data for?
Well, training data is like that. You see, I will put it over there. You see, we have tens of thousands of protein interaction data out of there from the protein data bank, and then we add some particular mutation data as a training data too as well. So those are about and then some other data is the so-called deep mutation scanning data related to SARS-CoV-2.
So those protein interactions in the protein data bank, are they generic or are they specific to?
Most of the generic, but there are some ones related. Later on, we found out more data related to SARS-CoV-2. Right. Yeah.
Next question. I was wondering, the Laplacians have strictly more information than the barcodes. So it's the barcode plus more.
Yeah, exactly. That's enable you to see the subtle difference, right?
Mm.
Yeah.
No more questions? One quick question.
On a lighter note, so what variant will be next dominant?
Sure, we have a lot of predictions about that. At this point, you see, my people, they got to become a professors, you know. That's my team. I need to regroup my group. That's a part in the academic research. You have a group doing something, and then people become a professor, go outside, they have to do teaching, you know, the whole thing go to a stop. But anyway, FDA, they are interested in the, not only FDA, also CDC is interested in our code. They take our stuff over the day and then hopefully they can keep it doing the prediction. Right. But sure, if I really wanted to put a resource over there, we can get it, everything going again in a couple months, right?
All right. Let's give the speaker another